for coming, everybody. So today the plan is to do like this kind of like workshop about the ZK-EVM. We all know a lot about the ZK-EVM. We've been working on it for like years. And like the idea today is to have like less presentations and more like talking. And we want to put some structure around the talking, but we don't want to stop people from exploring. So the idea is that in the morning, we're going to talk about our various different efforts. We're going to have 3 presentations, the ZK-EVM community effort, the Hermes Polygon effort, and the consensus effort. But and then we're going to break out into like separate groups where you can like ask questions / interrogate other people about their approach. And like the idea here is to just have some time to sort of dig into what other people are doing. We're also open for other people to have these kind of breakout groups. If you want to participate in such a breakout group, you can just add your group to this list. So I was thinking in the morning we would focus on like just actual implementations, and in the afternoon we were going to dig into more like specific primitives that we share and use. Cool. Okay, so the next thing that I need to do is do the presentation. But if anyone wants to edit these slides or edit this document to put your working group, feel free. And at the end of the presentations, I'll come back and we'll just go through the list, and someone can volunteer as the point person for that kind of working group. Cool. Okay. Okay. Full screen. That's so weird. Okay, that's right. How do I do full screen?
Top right slideshow next to the share.
Oh, okay. Thank you. Okay. Okay. So this is our approach to ZK-EVM. It's very similar to other approaches, and I think that this presentation is short because you all probably know a lot of what we're doing. I just want to give a like brief introduction, and then other people can do theirs, and then we can sort of dig a little bit deeper. Cool. Okay, so like it's a team effort with like a community of different people. There's some people from the Ethereum Foundation working on this. There's some people from Scrolltech. There's some people from Loopring. There's some people from like other independent groups and other organizations that are participating that weren't able to make it here today. We're happy to have more people involved. We're happy to collaborate more with other people doing other implementations, and like maybe that's one of the things that can come out of today's meeting. Deeper descriptions and information is in the docs here that you can see. Like our goal is to make 100% EVM compatible ZK rollup / ZK-EVM, and we actually have 2 goals. Like ZK rollup is one, and the other one is we want to make a proof of validity for all of Ethereum's history. And the goal is that like this will help us with light clients. This will help us with finality, with like people querying data. Like it would be really cool if we could have like a Substack. Like when you go to the graph, you get a ZKP in response that says, hey, this is all the correct data. And like we can do this with MPTs and like proofs of MPTs, but that's a little bit less interesting because most of the stuff that you do on the graph is like check view functions, and you actually need some execution in order to calculate the correct thing to return. That's one thing, and like the other kind of big goal, and like we're not sure if we're going to do this or not, but like one thing that we consider doing is maybe moving the EVM into like outside of the kind of core piece of execution infrastructure, and have it more as like a separate thing that's used for that like uses the data availability of Ethereum and is like less part of the core Ethereum, but it's more like just like another L2. Although this wouldn't be like an L2 that would compete with the L2s that you all are making. This would be an L2 that's like very, very limited. It would maintain the same kind of gas block limits and state read-write limits that we have today, which are super conservative. And the place to innovate would be like the stuff that you all are doing. Cool. Yeah, so because we want to be 100% compatible, this means that we do a lot of difficult stuff. We do like the Merkle-Patricia tree, and we're going to have a presentation from Mia about that later. We also do Create 2, we do Catch-Hack, we do all of the difficult things that the EVM is doing. Cool. We take like a modular approach. So like some of the groups that are part of the ZK-EVM community effort are working on like using a different tree instead of MPT, or using a different hash function for storage. And like our approach is that we kind of break these pieces out so that you're able to switch them in and replace them. So right now we're working on like just implementing a basic version, and then from there we're going to consider like what is the thing that we need to optimize for. There's a whole bunch of different things that we need to consider, and like it's unclear exactly what we're going to want to do. Do we want to optimize for the gas cost on layer 1? Do we want to optimize for the prover time? Do we want to optimize for implementation complexity, simplicity? And there's a whole bunch of different things. And like I feel like once we get to the point where we have like provers running and things, we'll get a better sense of like, do we really care about spending X amount on AWS every week, as opposed to like having a super complicated circuit that's hard to audit, or having higher layer 1 gas costs. Cool. So I'm gonna finish up really quickly now, because I think it's close to the end of my time. So we have a bunch of different components, and like the EVM circuit, state circuit, bytecode circuit, TX circuit, and like all of these different components kind of talk to each other. So like why do we break them into the simple components? And the reason for that is that it's like, when we break things into simpler components, it's easier for us to like separate. It's easy for us to reorder operations. Like if we order operations in the EVM proof by the program counter, it's easier to do some stuff. But if we order things in the state circuit by like the index of memory that's being read from or written to, it's easier to do the state circuit. So like when we do that and kind of separate concerns, things get easier. It's also we can make it a little bit more efficient. So how do the things talk to each other? Well, we have all of these lookup tables where like you basically in the EVM circuit you can look into the state circuit, and in the state circuit you can look into the catch-X circuit, and we end up having this like connection of all the different components, and this is how they sort of talk to each other in order to make the full proof. Also in the EVM circuit we have this kind of finite state machine that we use to like process TXs, and like we just need to know what state we're in so that we're able to like continue the execution. Cool, that's it.